We're going to continue our exploration of decision making and classification by looking at the concept of a decision boundary. And this is a concept that in a sense we've already seen, but we're going to make it a little bit more explicit. In 1D, it's actually fairly straightforward. So let's go back to our original single feature model for the prediction of whether our team is going to win or not. And so in this case, our single feature when we looked at the 1D model was the field goal percent difference between the two teams. And so this is how we would write it. The probability of our team winning is given by the logistic function applied to the field goal percent difference multiplied by a coefficient which we would have to find by maximum likelihood estimation, right? And so the dots are our data. This is our label data. This is a supervised learning problem where these are the cases when the team lost and these are the cases when the team won. And this is the best fit for the curve that we have based on our actual estimate of the value of the parameter. So the next step, as we've already discussed, is picking a threshold, right? What do we want to classify as winning or losing? Once we've built the fit to the model, we find that our decision rule still needs to be enacted. Let's say that we pick a threshold of 0.3, arbitrary value. So once we pick a threshold of 0.3, we are classifying these points right here as being as losing, and these points get classified as winning. And what that does is it actually defines this point right here, even though it looks like a vertical line, it really is a point because it is the only thing that matters is this dimension, right? We're moving on a one-dimensional along a single dimension, which is the axis of our feature. And at this point, we transition from classifying any point that is to the left of this right here is classified as losing, and any point to the right is classified as winning, which means that point is what we call our decision boundary. This point happens to be at a value of roughly x equals minus 0.02. Think for a second where that value comes from. Where is that point? Well, that point is it's the inverse value of the logistic function at the point of our threshold, right? It is the inverse value of sigma for our value of the parameters at this point, because once we find this threshold, what we're saying is any value of our feature whose corresponding probability is less than 0.3 is classified as losing. So the decision boundary is connected to the inverse of our logistic function at that point. And we're going to see why this becomes a little bit more important when we switch to a two-dimensional case. So remember when we said, well, let's study what happens if we add more information to try to build a more sophisticated model. And so if we include not only the field goal percentage difference, but also the personal foul difference. So we added a second feature now, and in fact, we also have an intercept. If we look at the shape of our, excuse me, of our logistic function as a function of both variables, we have the surface for the prediction of our probabilities. And now the question is, what does the decision boundary look like? In 1D, it's a point. It's a single point, which is given by the inverse of the logistic function. But now what we're saying is once we choose our threshold, all points that are below this threshold will be classified as losing, and all points that are above are classified as winning. But the question of the decision boundary is not a question of what happens on this surface. It's a question of what happens on the space of the features. Just like for 1D, it was a question about what happens along this line. Where do we flip along this line from predicting loss to predicting win? Now the question is, what happens? Now we have this feature, but we have a new feature over here. What happens on this entire plane as we cross this threshold, right? Which points are classified in one way or the other? Because our data can be plotted as a function of this, of these two features on this plane. And so what we want to know is on that plane, which points end up on one side or the other of the prediction on losing or winning. And it turns out that this decision boundary in 2D is, obviously it's a line in general, but in this case it's a straight line. our decision boundary is linear. It's not just a line, meaning an arbitrary curve. It is a linear decision boundary. And we can actually see why that's the case. You might have some intuition already by looking at this picture that the intersection between the threshold and the surface looks like a straight line, and that is indeed the case. But we can show that. We can actually prove that very straightforwardly, because how did we construct our model? Well, we said the probability of being class 1 based on our features is equal to the logistic function applied to our linear model. Right? That is the construction that we made. So probability is equal to sigma of x transpose t. These are the actual values of the fit. And once we choose a threshold of probability, what we are saying is that this probability equals to 0.3 is where things flip from one value to the other. So the decision boundary is actually given by this equation. That may not look like a linear function because there's this sigma here, the logistic function, which is nonlinear. But remember what we did when we were in 1D, and we said, well, if this is sigma equals 0.3, then the inverse of this gives us the value of x where the decision boundary happens. Well, we can do the same exact thing here. We can take the inverse of sigma, so we can apply the inverse function of sigma on both sides. The inverse sigma of 0.3 is going to be just a number. Remember, these are the log odds, so we know exactly what this is going to be. We did that algebra in the previous lecture. So what we end up with is a function. In fact, this value is the value that we described already. This is roughly what inverse sigma of that is. It's a single number. And now, as an equation in terms of field goal percent difference and personal foul difference, this is a linear equation. These are just numbers, and this is a linear equation, and think of these as x and y. This is number plus number times x plus number times y equals number. As an equation in x and y, it's just ax plus by equals c. It is just a linear equation. Now, that tells us that this decision boundary is actually a straight line. If we then go and plot the data, if we plot the data with its correct labels on top of the decision boundary, then we have a very immediate visual representation of our false positives and false negatives, right? Because the decision boundary defines where do we cross from predicting loss to predicting win. So to the left of this decision boundary, our prediction is blue, which is that we predicted loss. And to the right of the line, we are predicting orange, which is the class 1, the team wins. But the actual points, some of the points over here in the orange region are themselves orange, meaning the team did win, and these are correct predictions. These are true positives. Some of the points on the losing side of the prediction are themselves actually blue points. They are correctly labeled as losing, and these are true negatives. But for example, this blue point right here is a point that was predicted as winning, but was in fact a losing game. So we predicted a win and when it was a loss. So this was a false positive. Our prediction was positive, but it was incorrect. So this is a false positive. And points like this orange one right here or this orange one right here are the opposite. These are points that are predicted as a loss, but they are in fact a winning point. They're orange, which means these are false negatives. So in here now you see these four elements of our confusion matrix nicely illustrated visually, right? These are the true positive points, true negative points, the false positive points, the blue ones who are living in the orange zone, and then the false negatives are the orange ones living in the blue zone. And so this concept of a decision boundary is an important one because it tells us what kinds, when we look at the data, right? If the distribution of the data is clearly separated, then maybe a method that leads to a linear decision boundary may be sufficient. But if we have a very complicated shape in the separation, we may need methods that are capable of representing a nonlinear decision boundary.